Hello students. Sequences and summations. A sequence is an ordered set of infinitely many terms. So you have a sub 1, a sub 2, a sub 3, a sub 4, etc. And there's infinitely many. And a sub n represents the nth term. Now sequences can follow patterns or not. If possible, find the next three terms of each sequence below. All right, 1, 5, 9, 13. To go from 1 to 5, you add 4. Well, it turns out that's exactly what you do to go from 5 to 9. Is what you do also to go from 9 to 13. So let's assume that that pattern continues and keep adding 4 to find the next three terms. We do 13 plus 4 is 17, 17 plus 4 is 21, and 21 plus 4 is 25, etc. 5, 6, 4, 7, 3, 8, 2, 9. This is an interesting one. It looks like it's kind of going back and forth. To go from 5 to 6, we are adding 1. To go from 6 to 4, we subtracted 2. To go from 4 to 7, we added 3. 7 to 3, we subtracted 4. We added 5. Then we removed 6. Then we added 7. So keeping up this pattern, I'm going to guess the next one is going to remove 8, add 9, remove 10. Remove 8 from 9 is 1. Add 9 to 1 is 10. And remove 10 from 10 is 0. The next one would have been add 11, then subtracted 12, and then added 13, then subtracted 14. The next sequence, 3, negative 8, 1, 0, negative 7, 21. When I wrote the sequence, I did not think of a particular pattern, so it's not always easy to predict terms of a sequence. No particular pattern emerges here, unless perhaps you found one that I wasn't thinking of. The next one, 3, negative 6, 12, negative 24. Looks like the signs are changing as well as we are doubling in size. So to go from 3 to negative 12, we multiply by negative 2. And that appears to be the case between each pair of numbers. Continue to multiply by negative 2. So we're going to do that again, then again, then again. So negative 24 times negative 2 is going to give me 48. 48 times negative 2 will give me negative 96. And negative 96 times 2 will give me positive 192. The next sequence, 1, 3, 7, 15. There could be a variety of things that happen. If we think of addition, we added 2 to go from 1 to 3, and then we added 4 to go from 3 to 7. So I'm guessing maybe we're going to add 6 next. Oh, but we don't. We add 8. So what we're adding doesn't appear to be growing by 2. It appears to be doubling. And so I'm guessing that the next one will be add 16, add 32, and then we're going to add 64 to get the next three terms. Adding 16 to 15 is 31. 31 plus 32 is 63. And 63 plus 64 is 127. You might have also noticed a different pattern here. It turns out that if you were to double a term and then add 1, you would get the next term. So double 1, we get 2, and add 1 to that, we get 3. Well, if we double 3, we get 6, and add 1 to 6, that gives us the next term. Double 7 and add 1 gives us 15. Double 15 and add 1 gives me 31, etc. So this is another pattern that appears to produce the same sequence. Now this last one, this one's called the Fibonacci sequence. It's a famous sequence. Maybe you've seen the Da Vinci Code. The way to get this is the first two terms are just 1 and 1, but then from there a pattern emerges. To find any one term for the third term and on, you add the two preceding terms. So 1 plus 1 gives us this 2. And then we do 1 plus 2 to give us this 3. And then we do 2 plus 3 to give us this 5, etc. 3 plus 5 will give me 8. And then 8 plus 5 will give me the 13. So to find the next one, we do 8 plus 13. That's going to give me 21. And then to find the next one after that, we do 13 plus 21, which will give me 34. And then after that, we do 21 plus 34, which will give me 55. And this is called the Fibonacci sequence. Okay, next slide. A sequence is defined explicitly if a formula for directly calculating the nth term is known. Find the first 5 terms and the 20th term of each explicitly defined sequence below. All right, so b sub n is equal to 3n minus 1. We're going to say that the n's are natural numbers. So we can say n is an element of the natural numbers. That's like saying that n has to be equal to 1, 2, 3, etc. So b sub 1, you plug 1 into both ends here. So this would read b sub 1, and this would read 3 times 1, which is 3 minus 1, which is 2. So b sub 1 would be 2. That's the first term of the sequence. b sub 2, the second term of the sequence. We just plug 2 into this. 2 times 3 is 6, minus 1 would be 5. b sub 3, plug 3 into the explicit formula. 3 times 3 is 9, minus 1 is 8. You might start to see a pattern emerge. It looks like all we're doing is adding 3 to go from term to term. So I'm going to predict that b sub 4 will be 11, and that b sub 5 will be 14. And then if we were to skip ahead in the sequence and say, what is b sub 20, the 20th term, then we can simply just plug 20 back into this formula. 3 times 20 is 60, minus 1 is 59. Now the next one is a sub k is equal to k over k plus 3. And let's also say that k is a natural number, and that k will say starts at 1. So that means our first term, plug in 1 for both k's. We're going to get 1 over 4. So we get 1/4 is the first term. Plug in 2 for all the k's. So we're going to get 2 over 5. So 2/5 is the next term. Plug in 3 for the k's. We're going to get 3 over 6, which you could write as 1/2, but we'll leave it as 3 over 6 to keep the pattern going. You can see happening is the numerators are growing by 1, and so are the denominators. So I'm going to guess that the next one here is just going to be 4/7, and the one after that will be 5/8, etc. And then when we get to the 20th one, the 20th term will be just plug 20 in for the k's here, and we get 20 over 23, etc. And for our third example, we have c sub I. This time, let's assume that I is a whole number, and the whole numbers start at 0, so 0, 1, 2, etc. Our first value will be when I is 0. So we're going to have a c sub 0, which will be our first term, and we just plug 0 in for all the i's here. We get -1 to the 0, that's positive 1, times 0, so that's 0, and then add 2, so we get 2. Then c sub 1 will be the next term. Plug in 1s for all the i's, we're going to get a -1 here, times a 1 is -1, plus 2 is going to give me positive 1. C sub 2, which will be our third term technically, -1 squared is 1, times 2 is 2, and add 2 gives me 4. Fourth term is c sub 3 technically, and we're going to get a -1 cubed is negative, times 3 is -3, and add 2 is -1. And our fifth term, plug in a 4 for all the i's, we're going to get a positive 1 here in the front, times a 4, then add 2 is 6, etc. Now let's skip ahead to what the 20th term is going to be. Now you have to be careful here because the first term was c sub 0. So the subscript is not indicating what term we're on. We have a first term, a second term, a third term, etc. And if I want to go all the way up to the 20th term, well, the subscript is one number less than the term. So I need to find the C19th term. And so we want to actually take our explicit formula and plug in 19 for all the i's. And -1 to the 19 will stay -1 times 19. So -19 plus 2 will give me -17. And then this sequence would continue. Let's go to the next slide. Find an explicit formula for each sequence below. And we're going to assume that we're going to start subscripts all at 1. So in other words, we want this first term to be our a sub 1. That's our a sub 2, a sub 3, a sub 4, etc. This next one we'll use b's. That's b sub 1, b sub 2, etc. And the last one we'll use c's. That's c sub 1, c sub 2. So let's just start all of our subscripts at 1 to be consistent. And a sub n, find some sort of formula we can put right here that will correctly give us these values when you plug in the different n's. If you were to make a table out of this, n and a sub n, so when n is 1, we want our first term to be 1. When n is 2, we want our second term to be 5. When n is 3, we want our third term to be 9, etc. Now you'll notice that we keep adding 4 over here when we keep adding 1 to n. This establishes a linear relationship. And so we could really just take the first 2 points and figure out what this linear relationship is. We can figure out a slope. So we have 5 minus 1 is 4, over 2 minus 1 is 1. So we have a slope of 4, and then we can use point slope form with this. Normally this would be x and y, right? So we would say y minus the y coordinate equals the slope times x minus the x coordinate. But it's not x and y, it's n and a sub n. So this would be a sub n and this would be n. This allows me to say that a sub n minus 1 is going to be equal to 4n minus 4, and then add 1 to both sides. So here's our explicit formula right here. And let's just double check that it works. Plug in 1 for n, and we get a result of 1. Check. Plug in 2 for n. 2 times 4 is 8, minus 3 is 5. We get our second term. Check. This table of data will be satisfied by this equation. This next one, the pattern here was multiplying by -2 to go from term to term. And we could say b sub 1 is 3. b sub 2 is 3 times -2. b sub 3 will be this answer times another -2. So you could write it as 3 times -2 squared. b sub 4, it's found by taking this one and multiplying by another -2. So you could say it's 3 times -2 cubed. Right, so we have b sub 1 is 3. b sub 2 is 3 times -2. b sub 3 is that term, and b sub 4 is that term. So the formula that I'm looking at here, I'm going to generalize from this last one. Looks like b sub n will be 3 times -2 to the, and notice the power is one number less than the number term we're on. So it looks like that this will be an n minus 1 power. And you can certainly double check this. Plug in a 1 for n. 1 minus 1 is 0. -2 to the 0 is 1 times 3 gives me the first term. Check. b sub 2. Plug in a 2 for n. 2 minus 1 is 1. And we get 3 times -2 to the 1. We get this term. Check. Etc. And then our c's. Okay, notice the numerators are decreasing by 1 and the denominators are increasing by 5. So our numerator is going to be a linear expression. Our denominator is going to be a linear expression. So c sub n, look only at the numerators. Our slope is going to be -1. So if you're going to do a -n, it will be involved. And then we need to add something here so that the first term comes out correctly. C sub 1, we want this to be a 5. Well, when n is a 1, this will be a negative 1. So what number is needed right here to make a 5 out of that? We'll need a 6. Let's just double check this for the numerators. Plug in n equals 1, and we get 5 out of this. First numerator. Plug in n equals 2. We get 4 out of this. Second numerator. Plug in n equals 3 into this. We'll get 3. Third numerator, etc. Now our denominator is increasing by 5 with each increase in n. So we have a slope of 5 for the denominator. So we'll have a 5n plus and then something. When I plug in 1 for n, I want this result here to be a 3. So if that something is a negative 2, in other words, put minus 2, this should work out. Now I'll just check the other denominators. Plug in a 2 for n. 5 times 2 is 10, minus 2 is 8. That works. Plug in a 3 for n. 5 times 3 is 15, minus 2 is 13. Check, etc. So this will be the correct formula for giving me all those denominators. This is the formula giving me all the correct numerators. And so therefore we have our formula to give me these fractions. Okay, next slide. A sequence is defined recursively if a formula for the nth term depends on preceding terms. Find the first 5 terms of each recursively defined sequence below. Okay, looking at the first one. Notice that there's a b sub n is equal to, and then on this side we see an expression that refers to the term right before b sub n. Be mindful that this minus 1 is part of this subscript. In general, if b sub n is somewhere in your sequence, then the one after it will be b sub n plus 1, the one after that will be b sub n plus 2, the one before that will be b sub n minus 1, before that will be b sub n minus 2. This establishes a relative position of b sub n with some of its neighbors. So this formula is saying that to find b sub n, to find this position, you're going to double b sub n minus 1. You're going to double the one before it and then add 1. But this is generally true. So to find any term of this sequence, you double the preceding one and add 1. Now b sub 1 is already provided. In fact, we need one term to be provided so that the pattern can be established. So we're looking for b sub 2 next. So we're really only going to use this formula for n is bigger or equal to 2. N is a natural number. So now b sub 2. So now take this formula and plug in 2's for all the n's. So you'd get a b sub 2 on this side, and this will be a 2 minus 1. So we're going to get 2 times b sub 1 plus 1. Well, we know b sub 1 is 3, so we can plug 3 in for that. And so we're going to get b sub 2 is equal to 2 times 3 plus 1. So double the one before it and add 1. That gives us 7. Now to find b sub 3, we're going to take this formula and change all the n's to 3. So b sub 3 is equal to 2 times b sub, change this n to a 3, minus 1 is 2. So b sub 2, and then add 1. Notice what this is saying to do to find b sub 3. Double the term before it, and then add 1. All right, so b sub 2 is the 7. And we get b sub 3 is equal to 2 times 7, which is 14, and add 1, we get 15. And now I'm going to just go with the pattern. B sub 4 will be double b sub 3, and then add 1. So double 15, which is 30, add 1. B sub 5 will be double the one before it, so double 31, which is 62, and then add 1 is 63, etc. Now this next one, notice this is expressed b sub n plus 1 is equal to 2 times b sub n. Remember that after b sub n would come b sub n plus 1. So this is still establishing a pattern that to find this one, you use the one before it. So we're going to double the one before it and then add 1. So this is the exact same pattern that we see established by this expression. The only difference here is that a different initial value. So this time b sub 1 is negative 1 as opposed to being 3. So the next one I want to find would be b sub 2. Well, look at your formula, the way it's written, and ask yourself what n you would need to use to create a 2 subscript right here. Well, you would need n to be 1. So we actually got to use this formula for n is bigger or equal to 1. So when n is 1, we get b sub 2. When n is 2, we get b sub 3. When n is 3, we get b sub 4. To find b sub 2, I want all the n's in the statement to be 1. So b sub 2 will be found by doubling b sub 1 and then adding 1. But this time we have a different initial value. We plug in a negative 1 in for b sub 1. So we get 2 times negative 1, which is negative 2, and add 1 is also negative 1. Well, that's interesting. So this particular pattern didn't change our term. Well, b sub 3, take the formula and change all the n's to 2, and you're going to get b sub 3 equals 2 times b sub 2 plus 1. All right, so if you double negative 1, you get negative 2, and add 1, it stays negative 1. Well, b sub 4 is also going to be negative 1. B sub 5 is also going to be negative 1. This particular sequence is just a sequence of negative 1s. It's called the constant sequence. If you were to write it out, it would just be negative 1, negative 1, negative 1 forever. Okay, the next one. A sub k plus 1 equals a sub k times k minus 1. And a sub 0 is given. So this time we're assuming that a sub 0 represents the first term. So our next term would be a sub 1. Well, again, we have to ask ourselves, what value of k would be the k that would give me a 1 subscript right there? And that k would be 0. We get to use this formula for 0, 1, 2, etc. So take this statement and change all the k's to 0. That would give me a sub 1 on this side. And over here would be a sub 0 times 0 minus 1. And we have recursion going on because it depends on a prior term. First term had to be given for us to even continue the pattern. So this gives us a -1 there times another -1, so we get a +1 out of this. Now let's go to the next term, a sub 2. To make a sub 2 on the left side of our general formula, we need the k's to be 1s. So change all the k's in the statement to 1. And that gives you a sub 2 equals a sub 1 times 1 minus 1. And the a sub 1 we just found, it's the 1. A sub 2 will be 1 times 0, so we're going to get 0 for a sub 2. Go for a sub 3 next. Take this statement right here and change all the k's to 2. So it's going to be a sub 2 times 2 minus 1. But a sub 2 is 0. So a sub 3 will be 0 times 1. It's also going to be 0. Oh, does this mean that we're going to get 0 from here on out? Let's see. A sub 4 is equal to, formula would give us a sub 3 times 3 minus 1. But since a sub 3 is 0, that's going to 0 out. And technically I'm done. The first term of the sequence was a sub 0, so it's -1. Then we got +1 was a sub 1. And then a sub 2 was 0, a sub 3 was 0, a sub 4 was 0, and we can expect zeros from here on out. And there's the first 5 terms of the sequence. We stopped at a sub 4 because we started at a sub 0 in this case. And the last one is a recursive formula where c sub m is found by taking c sub m minus 1 and adding it to c sub m minus 2. Now in the pattern, c sub m is here, the one before that is c sub n minus 1, and the one before that is c sub m minus 2. So what this general formula is saying to do is to find this term, you add the 2 prior terms. Well, this is the Fibonacci pattern. And so the first 2 terms have to be given. It's not enough to just give you the first term. We have to have the first 2 terms. So our pattern really starts to kick in for c sub 3. So in other words, this equal sign, we're only going to be using this pattern for m is bigger than or equal to 3. Plug in 3's for all the m's here, and this would read c sub 3 is equal to c sub 2 plus c sub 1, which is why we had to know the first 2 terms to even begin. Add those together, and we get 2 out of this. C sub 4 will be found by doing c sub 3 plus c sub 2. We're going to be adding c sub 2 and c sub 3, so adding 1 and 2, and we get 3. And finally, c sub 5 is going to be found by doing c sub 4 plus c sub 3, and c sub 4 and c sub 3 are those 2 numbers, add them together, and we get 5. If you had changed one or both of these initial terms, then we would be getting different numbers here, and this technically would not be the Fibonacci sequence anymore, but be something similar to the Fibonacci sequence. Okay, the next slide. Summation notation can be used to represent sums as demonstrated below. Find the value of each sum below without technology if possible. Okay, so first thing we're going to do is cover a few bits of terminology. This big E thing is actually an upper Greek letter, and it's a sigma. A lowercase sigma looks like this. Now the K could be really any letter, but it's called the index of summation. The 3 is the starting value, and the 8 is the end value. And the starting value, you want it to be an integer. So the symbol for the integers, if you recall, is the bold Z. Same thing's true for the end value. You want it to be an integer. And then the other part of this is, next to the sigma is what's called the summand. It's an expression that involves the index of summation. Okay, how we compute this sum is we begin by plugging in the starting value of the index of summation into the summand. So you plug k equals 3 into the summand. 2 times 3 is 6, minus 1 is 5, and you get a result of 5. And then you add. And that 5 we obtained when we let k be 3. Now we're going to let k be 4. And we're going to go through every integer until and including the use of 8. So the next one is going to be plug in 4 right here for all the k's in the summand. 2 times 4 is 8, minus 1 is 7 plus. There's going to be a k equals 5 term. There's going to be a k equals 6 term, a k equals 7 term, and then we're going to finish with the k equals 8 term. Okay, plug in 5 for all the k's. 2 times 5 is 10, minus 1 is 9. You start to see a pattern. This is a pattern of addition by 2. So this is going to be an 11, this will be a 13, and this will be a 15. You should confirm all of these are the correct terms you get. And then if the numbers aren't too large, go ahead and do this by hand or reach for a calculator. Or if you do grouping like this, this is clever. 5 plus 15 is 20. There's another 20, and here's a final 20. So there's 20, 20, and 20, so this should add to 60. Okay, let's do a few more of these. N equals 0 to n equals 5. Well, let's plug in 0 for n, and when n is 0, we get a 5 out of this. Then there's going to be an n equals 1, there's going to be an n equals 2, an n equals 3, an n equals 4 term, and then we're going to finish with an n equals 5 term. So plug in a 1 next, right here, and that's going to give me a 7. Now plug in a 2, will give me a 9. And notice that this actually is going to represent the exact same sum we just had before, just expressed a totally different way. So this will be 60 again. So these two sums, even though they look very different, represent the exact same sum. Another thing to point out is how many terms are in the sum. Some people suppose that the 8 means how many terms there are, but notice that there are not 8 terms here. There are only 6 terms here. So you might say, well, okay, well, I do 8 minus 3, that's going to give me 5, and you might guess that we have 5 terms, but there's not. There's actually 6 terms. If you do 8 minus 3, that you do get 5, but that tells you that there are 5 steps to go from 3 to 8. But when you're counting these numbers, 3 through 8, you have to do 8 minus 3, but add 1. So the number of terms will be the ending value minus the starting value, add 1. Notice that's also true here, right? Do 5 minus 0 is 5, and add 1 is 6. So again, we still have 6 numbers in this sum here. The next one, plug in m equals 4. That's our first one. So we have -1 to the 4 plus 1. Well, 4 plus 1 is 5, and -1 to an odd power is still negative. So we have a -1 up top, and plug in 4 for the m in the bottom. Now plug in m equals 5. 5 plus 1 is 6, and -1 to an even power goes back to +1. So add a 1/5. And then we're going to add a -1/6. So you can just say subtract 1/6. Then we're going to add a +1/7. And then we're going to subtract 1/8. Now we keep this up until, and let's just write the last 2. The one before 21 would be 20. And so plug in 20 everywhere here. We're going to have an odd power, so it's going to be subtraction, and this will be 20. So we're going to have a -120 as the second to last term. And then when m is 21 will be the last term, plus 1 over 21. This is when m was 4, this was when m was 5, etc. This was when m was 20, and this last one was when m was 21. Well, how many fractions are in this list? Well, we do 21 minus 4, which is 17, and add 1, and we get 18 terms. Now, I don't care to add these together by hand because all the denominators are different, and getting a common denominator is going to be very challenging. But I will do this one with technology. I want to show you how Desmos can be used to do sums. Here, you can look for the Greek uppercase sigma and the functions under miscellaneous. You can find it right there. Or you can just type in the word sum. Now, it defaults to an n index of summation. If you want, you can change it to a different letter, like m. And our m started at 4, and it ended at 21. And then for the summand, I recommend you always put the summands in parentheses, where our numerator was -1 raised to the m plus 1. I'm going to put some parentheses on that too. And then all of this over an m. And here is the number we get, -0.1169. And this last one, so our index of summation is I. I starts at 22 and ends at 231, so there's going to be lots of terms here. But notice our summand has no I. Our summand is a constant. What this means is that you're just going to keep adding 2. And the question will be, though, is how many 2's we add. The first 2 will come about when I was 22. The second 2 is when I was 23, and then when I was 24. And we keep this up until we get to I is equal to 231. So because they're all 2's, all we have to do is figure out how many terms there are here. And we can do that by saying the upper number, 231, minus the lower number, and add 1. And this gives us a total of 210 terms. And since each term is a 2, we can simply use multiplication to finish this. We can say there's 210 2's, so we just do 2 times 210, and we get 420. Express each sum using summation notation in 2 different ways. Okay, so here we have an alternating sum. We're going to have a sigma. Let's go ahead and just use k as our index of summation. It doesn't matter. We do have to figure out a starting and an ending value, and then, of course, our summand. And we can also make an assumption that we want k to start at 1. If k starts at 1, then we want this to be a sub 1. We want -16 to be a sub 2, 32 to be a sub 3, -64 to be a sub 4, and 128 to be a sub 5. In the alternating signs, let's take care of that part first. And the first term is positive. So let's get a -1 raised. Let's put a k here and see what happens. And when k is 1, we're going to get a negative first result. We don't want a negative first result. We want a positive first result. So one way to offset this is to add a 1 to that k. We plug in k equals 1. That gives me a 2. And -1 squared is a positive. This will guarantee that we get the plus minus in the correct order. Now we have an 8 to begin, and then it appears to double. So we have an 8 times 2 to the k. This will be an exponential growth, and let's test it. If you plug in a 1, this will be a 2 to the 1. That's going to give me a 2 times 8. We're going to get a 16 to start, not an 8. Well, there's a couple ways to fix this. You can change this 8 to a 4 and test it again. When k is 1, we now get an 8. So all of this yields the first number that we want, 8. Let's test it when k is 2. When k is 2, this will be negative. This will be a 2 squared, which is 4, times that 4 gives me the 16. So -16 works out. When k is 3, we get a positive out of this. This will be a 2 cubed, which is 8 times 4, gives me that 32. So this will work. The question will be, though, is at what value k do we end? If we start at k equals 1, then the upper number will be the number of terms we have, right? Because if you start at 1 and end at 5, then 1, 2, 3, 4, 5 gives you 5 terms. Only when the starting value is 1 will the upper value tell you also how many terms there are. And well, this has 5 terms. So right away I can deduce that this has to be an ending value of 5. So here's one answer. Now, without changing the index of summation, let me go ahead and give you another answer that would work out well. You could have done a k minus 1, this would have worked. And you can also change this back to an 8 times a 2, but put a minus 1 on that k. Let's see if this works out. When k is 1 first, plug in a 1 for k, this becomes positive. Plug in a 1 for k, that's 2 to the 0, which is gone, which gives me the 8. So we get the positive 8. Check. Plug in a k equals 2. This will be 2 to the 1, which is just 2 times 8 will give me the 16, and this will be a negative. So we'll get a negative 16. Check. So this also works. Another one that we could do. You can also have this so that it starts at a different value. If you want this to start at k equals 0, for example, then we're going to have to offset all of our k's. And we can no longer end at 5 because that'll give us too many terms. If I remove 1 from the starting value, you need to remove 1 from the ending value. So this should be from 0 to 4. And that will give you 5 terms still. 4 minus 0 is 4, add 1 is 5. 5 terms. What you should do is now replace each k with a k plus 1. Well, if I change this k to a k plus 1, in other words, I make this a k plus 2, and change this k to a k plus 1, and then remove that 1, so this will just become a k, this should work out. Let's test it. Plug in a 0 for k. This will be a positive 1 because the exponent will be even. And if k is 0, then that's 1, so we get 8. So we get positive 8 out of this. Check. We get the first term. It works. Plug in k equals 1. This will be negative, and this will be 16. It works. We get negative 16. This does give us all the correct terms still. So if the starting and the ending values lower by 1, then all the k's you see here change to k plus 1. That'll offset the lowering of the starting and ending values of the index of summation. Also, we can say that k plus 2 is going to have the same effect as just doing k. And that's because negative 1 to the k plus 2 can be written as negative 1 to the k times negative 1 to the 2. Well, negative 1 to the 2 is always 1. If I change the k plus 2 to just a k in the statement, this is still a correct representation of our sum. So there's lots of ways you can do this. Now this next one, we have numerators increasing by 1, denominators increasing by 2. So we need to put a plus 2 here so that when you plug in a 1 for n, you'll get 3. When you plug in a 2 for n, you'll get 4. When you plug in a 3 for n, you'll get 5. So the numerators work out. Now let's get the denominators. Now the denominators are increasing by 2 every time, so we need a 2n. And then when I plug in n equals 1 here, I need this to be a 5. So let's do 2n plus 3 and then see if this works. Plug in a 1 for n, you get 5. Plug in a 2 for n, you get 7. A 3 for n will give you 9, etc. And a sum from n equals 1, and we just got to figure out what this final value is. Well, if the final is 15 over 29, you have to ask yourself, what n would you plug in to get 15 over 29? Well, this is easy, just look here. What n would you need there to make that a 15? And that would have to be a 13. Let's test the bottom. 2 times 13 is 26, plus 3 does give me the 29. So we stop at n equals 13 to get this last term. So here's one way to do this. Let's shift our index to a different letter to make it m, and let's start it at 4. Okay, so right here we see that we added 3. So you want to make sure you also add 3 to your ending value. So this needs to be stopping at 16. And the change we need to make over here with the ends, we need to change n, and I've increased the starting and ending values by 3, so I need to change n's to m minus 3's to offset that. And that would give me the following. We'd have an m minus 3 and then plus 2 over a 2 times m minus 3 and then plus a 3. And then if I simplify this, minus 3 plus 2, so that just gives me m minus 1. Distribute the 2, we get 2m minus 6, but then add 3, this is going to be 2m minus 3. This is another acceptable way to do the exact same sum up above. Notice when you plug in m equals 4, and we get 3/5 is our first term. Now plug in m equals 5, and we're going to get 4/7 next term. And we're going to finish by plugging in 16. Plug in 16 for m. So we're going to get 15/29 will be our last one. And this concludes our lesson.